Thanks all for joining. We're going to give it a couple minutes to enable all participants to come online, and then we'll get underway. Thanks all for joining. We'll get underway in just a moment. All right, let's jump in. Welcome to our Secretary Speaker Series, and thank you very much for joining. My name is Wade Crowfoot, and I get to serve as California's Natural Resources Secretary. These conversations, these speaker series are an opportunity to speak to experts, leaders, big thinkers on priorities and emerging issues in California. And we have a very special discussion today. If this is your first time, welcome. And if you've participated before in one of these discussions, welcome back. For those who have joined before, you know that there are a few ways that we try to maximize the interactivity of our Zoom discussion here today. First of all, we'll use the chat function to provide more information on our speakers and their affiliations, as well as information that arises in discussion. My colleague Geeta Chandra, who deserves the credit for organizing these discussions, is staffing the chat function. And so if you keep that open on your screen, it's helpful because she'll populate that chat function with a lot of good information. We'll also use the Q&A button at the bottom of your screen. So at any point during this hour-long discussion, if you have a question or a comment, you can click the Q&A button, type it in, and send it to us. We'll see that as panelists. Some of those questions we'll answer directly via the keyboard. And once we do, everyone will see both the question and the answer. And then sometimes the questions are really good to pose to the panelists, particularly at the end when we come back together as a group of panelists. We are recording our discussion today, so if you come back to our website by tomorrow, Natural Resources Agency website, you'll have a recording of this discussion. We'll also have a printed out or written out or document where you'll have all of the information provided in the chat function. Sometimes people like that information and you don't have to take notes. You can find that where you'll find the recording. So again, huge thanks for joining. We know that California is on the front lines of climate change, whether that's accelerating impacts on wildfire, drought, flooding, heat level, extreme heat, or sea level rise. And no geography is maybe more important or more impacted by climate change than the Sacramento-San Joaquin Bay Delta. It's one of the largest estuaries in the Americas, this meeting place of freshwater and saltwater. It's one of the most biodiverse places in the United States, with one of the richest varieties of plant and animal life. It's incredibly important to the people who live there and make their livelihoods there, both small towns and larger cities. And it's important to the state's water supply, given a large portion of fresh water supply for the state flows through this delta. It's also severely vulnerable to climate change, and that's where our conversation begins today. The Delta Stewardship Council is within our agency at the Natural Resources Agency, and its leader, Jessica Pearson, is going to kick us off here today. The Stewardship Council has led remarkable work, really working to build our understanding of the impacts of climate change on the Delta. and how we build the resilience of the Delta, its communities, its people, its economy, its diversity, biodiversity, its infrastructure to climate change. So welcome, Jessica. You're floating over the Delta as we speak. And just want to ask you to, if you would, lay the groundwork for over almost 250 people we have here in the discussion today about the Bay Delta or the Delta, as well as the climate impacts on the Delta.
Thanks, Wade. Far too often, the Delta is overlooked when it comes to climate conversations. So thank you so much for convening this important series. And thank you to everyone who's taking your lunch hour to tune in. The Delta is seeing change, just like everywhere else, from shifting weather patterns and sea level rise to evolving land use and demographics. I mean, the Delta reflects many of the same challenges and opportunities that are facing the rest of the state. So what makes the Delta unique are the stakes, as you've laid out. You know, all of this change is happening at ground zero for our state's water supply system. It's happening amid a backdrop of an already beleaguered ecosystem, and it's surrounded by flood-prone levees that protect people and farmland. So I was just reading an article about how humans have a negativity bias and how it's evolutionary, and historically it's helped keep us aware of danger and alive over the centuries. But when it comes to climate resilience in California, I like to think it's helpful to have a positivity bias. I mean, like, we can do this because we have to do this. Anyway, for people who aren't familiar, thanks for introducing the Delta Stewardship Council, Wade. We are the independent California state agency that's charged with advancing the state's co-equal goals for the Delta. And those co-equal goals are a reliable statewide water supply and a resilient Delta ecosystem. And the legislature told us to achieve those goals in a way that also protects and enhances the Delta as an evolving place. So it's important to note that even back in 2009, the legislature used the phrase evolving place to describe the Delta. And I think I have a map of the Delta that we were going to queue up here. Thank you, James. So what's at risk in the Delta, and why should people care? We talked about water supplies. For 27 million Californians are passing through the Delta. And the same goes for water that's irrigating vast acreages of agriculture. So, and then of course, people live, farm, and recreate in the region. Some people may think, hey, I know about the Delta, I've heard about it, it's complicated, but I don't really live there, so it doesn't really affect me. But the reality is that for most Californians, they are connected to the Delta in some way. They rely on it in some way through their water supply, their job, or through the food that they eat. So to protect the Delta's resources long-term, we've created and we implement the state's Delta Plan. So this is a management plan for the region. It's so many different groups are working within the Delta. So a single blueprint avoids chaos, and it gets us to those co-equal goals that are so important. And as you'll hear a lot about today, we focus on science to ensure that the decisions that we make are likely to be the right ones. So at the council, we keep building on the foundational work that is in the state's Delta Plan. We've recognized that climate change is a significant threat to our water future for a long time. So in a way, that's not news, but conditions are changing differently and more rapidly than we originally expected. So the good news is we keep learning, we're building new tools, and those tools give us advantages in managing the resources that we care about in the Delta and beyond. So on a personal note, I'm pleased to see the state of California really leading the way on issues of critical importance to society. Early in my career, I was lucky to get to work on the first ever climate adaptation strategy for the Department of Water Resources. And later, I got to help advance similar efforts at the Natural Resources Agency, shaping their first adaptation plan. That was back in 2009. So in my view, it's really remarkable to see how far California has come over the past 15 plus years. And now to see those early investments in science and planning paying off and providing the decision support that we need to adapt more effectively today, even when there's uncertainty. So that's the good news. Unfortunately, it's not all good news. In terms of the science, we now understand a lot more about vulnerabilities in light of climate change. We're seeing different types of extreme events like wildfires having greater impacts now than in the past. For example, California's 8 largest wildfires occurred in the Delta's watershed within just the last 7 years. Temperatures are continuing to rise. We're seeing more heat waves happening not just in the summer, but in the spring and the fall. We also recognize that extreme events sometimes happen in combination or in a series, like a strong storm can follow a catastrophic wildfire, and we need to plan for that. And as I mentioned, we now have significantly better tools to detect changes and project future conditions for critical components of our water supply and our ecosystems. So one initiative that I'm very proud of is the Delta Stewardship Council's Delta Adapts. This is a planning effort that synthesizes years of research and outreach in order to document the Delta region's assets, like its people, its ecosystems, its infrastructure, and then look at the vulnerability of those assets to extreme events like heat, flooding, drought. We essentially took a look at global models and expected impacts, and then we were able to downscale that to understand what it means in our backyard in the Delta. And then we basically crowdsourced with our agency partners and interested parties to collect and prioritize the actions that we need to act and adapt. So we have a pretty good idea about what will worsen as climate change progresses. For example, sinking land or subsiding land, levee breaches, extreme heat and flood events, water quality problems. And we're already hearing about these hardships from people on the ground, from farmers, from disadvantaged communities and tribes. But we have to grow increasingly comfortable taking action, even when we have uncertainty. And we really rely on science for that. So our agency, aside from the co-equal goals, we also have a mission to provide the best possible science. And to do that, we fund scientific research, but we also summarize and communicate science for others. So an example of that, we just released what's called the State of Bay Delta Science. This is a report that summarizes the state of the science on critically important topics. And so our latest edition, which you'll hear more about today, released in September, is focused on extreme climate and weather events, a series of papers, and lucky for you, you'll be hearing from some of those authors today. Finally, the council is also authoring a state-led report on the Delta for the upcoming 5th climate assessment. That's the first ever Delta-focused report from the 5th climate assessment. So we're excited about that and stay tuned for that in the spring. So what I hope viewers take away from today's conversation is really two-part. First, that science matters and is driving our decision-making. And second, the Delta Stewardship Council is working to coordinate across agencies and with others to address climate change and to protect the Delta and all of its uses.
Jessica, thank you so much. That was so helpful to both underscore the importance of the Delta, whether you live there or wherever you live across the state, and then explaining the Delta Stewardship Council and this role you play as this independent entity working to achieve balance in all that the Delta provides, and then really leaning in on the science and working to anticipate climate impacts. And we're very lucky to be joined by some remarkable scientists here today. So I think we'll move on to that. And I'm excited to bring you back in the conversation, particularly to talk a little bit more about, what is the science telling us we need to do? So next, it is my pleasure and honor to introduce Jayantha Obisekera. Jayantha, or Obi, serves on the Delta Independent Science Board. So he both is a contributing scientist to this body of knowledge, but he's also a director of the Sea Level Solution Center for the Institute of Environment for Florida International University in Miami. So Obi, you're a sort of an international national climate expert. Talk a little bit about how you've become engaged in this work in the Delta, and I think you're going to share with us a little bit more about climate modeling and what we know about impacts on the Delta.
Yeah, thank you, Secretary Crawford. I appreciate the invitation to speak for this series. Just to give you a background, I'm from Florida. I worked on the Everglades, and I have had the privilege of working in Bay Delta even before my tenure at the Independent Science Board. I worked on the National Academy panel about a decade ago, and I thought Everglades was complex. And when I went to Bay Delta region, I realized this is even more complex, and I really have a respect for the complexity and appreciate the challenge. Anyway, what I'm going to do today is it's basically based on a symposium we had in September. Like Jessica said, Delta is evolving, so is climate. and the science is evolving. We realize we need to basically understand the science, where it stands today, and what are the advances that have been made in the past decade, and how those advances could shape the adaptation. And finally, what we need to do to stay ahead. So next slide, please. I group what we heard at the symposium and by reading some of the state of science papers and others into four categories. These are compounding in terms of effects on the water and natural resources. One, you see on the upper left, you see the warming trend. Globally, about up to 1.5 degrees C, possibly 3 degrees by 2100, even could be higher. And this could have significant impact. And by the way, I'm not going to talk in detail about the technical aspects because some of these esteemed panelists who will follow me will probably cover some of those. One aspect that is of interest to me is the ability of the moisture atmosphere to hold more moisture in a warmer atmosphere. And for every degree of Celsius, the atmosphere can hold about 7%. Now, that means that we will have less snow and more rain. And you see on the upper right-hand side, that means that is our natural storage, and we're going to see a depleting snow cover, and more in terms of rain, and maybe earlier or later, rain depending on the condition. And that means our natural storage is depleting. And one aspect is also we sometimes have rain on snow. That could mean flashy or flood. So this is very important for some of the flooding in the Delta tributaries, for example. You see on the lower left-hand side, the other aspect is the intensifying hydroclimate variability. Climate in California is more variable than probably any other place in the country. And we know now that the storms may be fewer, but they are more intense, like the atmospheric rivers you might hear about. They might be clustered together, like what happened in 2023. And the other aspect that is of interest to us is what we call the hydroclimate whiplash. In other words, the rapid change from a very wet condition to dry condition over a short period of time. And this actually happened in 1862 after the big floods. And finally, accelerating sea level rise is what we have known about for some time, has doubled over the 30 years, and the projections are, that it could go up to 3 to 6 feet. And all this together will stress the system. And I think we know that the future climate is one of extremes, and we need to be flexible and adaptive in terms of addressing this new normal that we are going to, a new baseline that we are going to have. Next slide, please. So we also wanted to know, what have we learned from the last 5 to 10 years? We knew some of those other aspects that I mentioned earlier for some time. Maybe we have quantified this better. So I have listed 5 things that we know we have made some improvements in terms of understanding the science. We have the ability now to do a better subseasonal, particularly the near term or 2 to 3 weeks of extreme events, particularly atmospheric rivers. And I think that is very helpful to manage the operations of the system itself. The next, we have better understanding of rare events, particularly the atmospheric rivers driving the system-wide changes. The third is the recognition of flash drought, this rapid succession or rapid change from a wet condition to a flash drought. And that is challenging because we don't have much time to respond. And this is what I call hydroclimate whiplash. And the idea is we might see higher frequency of these whiplash events, and obviously the connection to wildfire. And we also have better climate models now. The global models are very coarse. We have the downscaling now much more improved. We have a 3-kilometer hybrid model that allows us to do better assessment of these climatic conditions or future condition. And we're beginning to use artificial intelligence to, along with these models, to understand the science better. And finally, we also have a good understanding of when we might transition to what we call low to no snow condition. And there are some estimates it could happen 20 years earlier in the future, particularly after the mid-century. And we also have some time. I think the bigger changes might come after the mid-century when the emission scenarios might deviate from each other quite significantly. Next slide, please. So this science allows us to come up with development of adaptation strategies. One thing, we've been talking about uncertainties. I think we have enough knowledge on science that we can start thinking about adaptation. We should not be bothered by too much uncertainty and not being able to do anything. I think there are some things that can be done, are being done. First is the nature-based solution, particularly floodplain restoration, forest management. But one aspect that we heard at the symposium was there are things that we can do above the reservoir system in the tributaries. There might be a way to address this increasing, changing runoff conditions by focusing on, additional storage in these headwaters areas. And then the technology integration, and this is being done. I think we need to make use of these technology advances, aided by forecasting and modeling. How do we better operate the reservoir system we have using advanced warning system? And finally, not finally, the third aspect is the what is called or how do we make use of these excess flood waters and try to store them in some innovative ways, like the managed aquifer recharge that's being practiced even today. I think this is another strategy that we should be looking at. And finally, the adaptive management. We know we are going to have more extremes, and there is no such thing as an average anymore. And it's going to be even more variable than what we have today. How can we be more flexible and use risk-based management strategies to address this variability of volatility in climate in the future? Next slide. So what more should be done? I think we should think about not averages. We cannot use the historical data and then simply adjust them to account for changes in averages. We need to focus more on the average. And we heard this phrase, what we call a manage flush to get through droughts and vice versa. I think we are going to have this hydroclimate, the whiplashes. We need to learn how to manage those. We also realize that we need greater community engagement and co-production of knowledge. And I think we need to work with stakeholders and co-produce solutions and engage the community, for example, tribal communities. The third is we need to improve cross-agency coordination. I think not every agency have the equal knowledge or skill set. We need to do some capacity building to improve the cross-agency coordination. The fourth is more integration of compounding risk. Sometimes we do the modeling, but we don't look at these compounding effects of sequence of hazards like climate, seismic events, subsidence, and hydroclimate whiplash. And finally, we need to produce tools that with end user in focus, with information that could be useful for users. And that's kind of my very short presentation on a lot of science that we heard about at the symposium and elsewhere.
Obi, thank you. And you did such a good job at breaking down what it sounds like are complex global models of climate impacts. And then the Independent Science Board and others have downscaled that to really understand what those impacts will be in the Delta. And then you've gone a step further on, what are sort of categories of solutions and what should we keep in mind? So key takeaways include, adaptively manage, don't set ourselves into a static system, but manage these changes. And to your point, really adapt to weather whiplash. Don't manage to the average, really manage to what will be, swings in hydrology, it sounds like.
That's exactly right.
Yeah. Well, thank you. I'm looking forward to bringing you back into the group conversation. So speaking of swings in hydrology, we have an expert with us who's going to break this down a little bit more. Sasha Gershinov is a research meteorologist at the Scripps Institution of Oceanography. And Sasha, welcome. I think you're going to talk a little bit more about what we now know in California as these atmospheric rivers, these huge winter storms that come, and what they present and risk to the Delta.
Thank you for having me, Wade. Yes, I'll try to unpack some of the things that Obi mentioned. I'm a meteorologist and a statistician by training. You all know what a meteorologist is. For those of you who don't know what a statistician is, it's somebody who doesn't have enough personality to become an accountant. But that's exactly what makes me a climatologist, because climate is the statistics of weather. So I'm going to show you some statistics of weather. I work on various extreme events related to climate variability and climate change, and also the impacts. And today I'm going to talk with you about some of the results from a paper that we recently put together for the State of the Bay Delta Science Report, focused on atmospheric rivers and floods and California's changing hydroclimate. Well, first of all, I'd like to acknowledge the wild, that is to say, highly volatile hydroclimate of California. When we look at how variable annual precipitation in California is compared to what's normal or what's average, we see that it's much more variable than any place in the United States. And that is a result of the fact that it doesn't rain often in California, but when it does, it often rains hard. And, we have a narrow season in our Mediterranean climate to generate most of our precipitation. And a lot of that comes from these big storms we call atmospheric rivers. They're basically rivers in the sky, but instead of liquid water, they carry water vapor. When this particular one about a year ago generated a quarter of annual precipitation for last water year. Whether we get a very wet year or a dry year, and normal years are not typical at all, it really depends on how many of these big atmospheric rivers we get, or if we don't get any, we end up with a dry year. One of the things that's challenging is that we recently learned that atmospheric rivers are the agents of ENSO heresy. They do not dance to the tune of El Nino or La Nina, making our extremely volatile hydroclimate very challenging to predict on seasonal timescales. Next, please. Next, please. These atmospheric rivers can certainly turn streams into raging rivers in California, and it's indicative of how challenging it is to manage water resources in the state. Next, please. Next. Atmospheric rivers, maybe one back. There are several of them at any particular time around the world. You can see the filaments of water vapor on this image here from space. There are anywhere between 4 and 7 of them or so at any particular time. An average atmospheric river moves the amount of water vapor that's equivalent to, on average, about 10 Mississippi rivers worth of discharge of liquid water. So when one of these hits a mountainous coast such as California, that water vapor is squeezed out. I'll talk a little bit more about that later, but basically our biggest floods are typically associated with atmospheric river landfalls. Next. And if we look at how our hydroclimate is projected to change, it really helps to look at daily precipitation, frequency, and intensity. And what's shown here are basically changes of frequency of precipitation that's binned into intensity bins from dry days or zero precipitation on the left to drizzle and heavier precipitation as we move to the right. And at the end, we basically, and we see that the dots show that we are expecting, and this is a very high confidence expectation, a decrease in precipitation frequency of kind of run-of-the-mill precipitation events and an increase in precipitation intensity and the frequency of really heavy and intense precipitation days. And if you look at the shaded bars, they show the contribution of atmospheric rivers to these changes. And they're basically atmospheric rivers are responsible for the change, for the enhancement in the extremes, whereas other types of storms are responsible for the decrease in the frequency. Next, please. And next. And this obviously means that atmospheric rivers in the future are expected to be even greater contributors to total annual precipitation, meaning that our highly volatile hydroclimate is expected to become even more volatile. And this also translates into specific storms. So here, for example, we estimated the return periods of a storm, basically the New Year's 1997 storm that dumped close to 20 inches of precipitation in the Yuba River Basin, and from about a 125-year return period event towards the end of the century, we expect that event to become more like a 60-year event. Next, please. So it's very helpful. So basically, I'm showing statistics that help to explain how this extreme volatility in our hydroclimate is expected to be exacerbated by climate change, and specifically on atmospheric rivers on steroids in the future. We haven't seen these changes yet, mind you, and that's important to underline. Next, please. So the role of our mountains cannot be underestimated. It's really the topography that squeezes moisture out of atmospheric rivers, causing rain and high mountain snow. Atmospheric rivers are warmer storms than other storms, so there are higher snow lines, more runoff in the future. Next, please. In a warmer climate, as Obi said, atmospheric rivers are going to carry more water vapor. And when you hit the same mountains with wetter atmospheric rivers, you get higher snow lines. Next, please. And more precipitation. Oh, if you could go back, I don't think my figure there showed very well. I thought that was going to show better. But basically what we're seeing in the graphic is a projection for less snow, and especially at low and mid elevations, and more rain, more precipitation on average, but less snow basically, and more precipitation means more rain, more runoff, and more propensity for flooding in a warming climate. Next, please. Well, it's a lot of text, but we can boil it down as far as the hydroclimate is concerned. To summarize, next, please, into a short statement from our report, and basically, it basically boils down to the fact that California will need to learn how to derive even more of its future water resources from less reliable snowmelt, fewer storms, and more punctuated floodwater. Next, please. And this is the final slide. Next. Yep, that's it. And I'd like to finish with a couple of positive statements. And one is that California has learned how to deal with this extremely volatile hydroclimate, and so we're better positioned to deal with future higher volatility in the state with proactive programs and evolving programs such as FIRO, forecast and informed reservoir operations, coupled with MAR, managed aquifer recharge, and flood MAR. And basically, we are already beginning to learn how to derive more water resources from floodwater while protecting us from flooding, more flooding in the future. And another thing that's important is although clearly our changing hydroclimate is going to make managing water resources even more challenging in the state, but at least we will have some precipitation to manage, whereas other Mediterranean climate regions are projected to dry in a much more severe way.
Yeah, Sasha, thank you for that. It's so helpful to understand just how robust your work and scientific work on understanding what the future hydrology will look like. And it sounds like there's a high level of scientific confidence that these atmospheric rivers will over time, provide a larger portion of our annual precipitation than they have. So to your point, maybe the silver lining is we have continued precipitation to manage. It just comes more intensely in a more punctuated way, and we have to figure out really how we protect people when it comes, and then be able to utilize it for those periods of dryness. Is that fair?
That's exactly right.
Yeah.
You've summarized my talk,
Okay.
Wade.
Thank you
Very
so much. And thank you for all the work. I mean, this is incredible to have this level of scientific caliber and expertise helping us understand the impact. So we're going to next go to another remarkable scientific expert, and that is Clifford Dahm, Professor Emeritus of the University of New Mexico and the former Delta lead scientist. Cliff, thank you so much for joining. You too have an appropriate Delta background here today. Talk a little bit, I think you're going to talk a little bit about the effects of wildfire and water quality in the Delta watershed. And when a lot of us think about the Delta, we think about water, we don't think about wildfire. So can you help us understand the connection there?
I'll do my best. Certainly, wildfire is something that has become increasingly an issue in California and throughout much of the world in the Western United States. As you mentioned, I came from the University of New Mexico. I had started a research project about the time that I came here to California, only to find out that the watershed that I was studying using some new advanced sensor technology was the source of the largest fire New Mexico had ever seen. And it burned most of the catchment that we were working in. And then I come back here to California, and the same kind of changes have occurred here in California relative to the frequency, intensity, and duration and size of fire. I first wanted to thank my co-authors on the paper that we wrote for the State of Bay Delta Science. Randy Dahlgren, retired from the University of California at Davis, was a major contributor. He's a very an amazing scientist when it comes to looking at how these kind of fire events affect water quality as it relates to drinking water. And so his work is focused on the drinking water effects that are mostly deleterious. And then Denise Colombano, who is a scientist here at the Delta Stewardship Council, also has increasingly gotten interested in this and has been a real source of getting information. If you would put up my first slide, please. Thank you. This map is an attempt to basically provide some summary information about California wildfires. Jessica Pearson already has done a good job of summarizing this. The top 8 largest California wildfires have occurred between 2018 and 2024. This is from a database that goes back to 1932. So these 8 fires spread through different parts of the Delta watershed. The one thing about all of them is that they have at least a partial footprint of the burn scar is within the Delta watershed. And the intensity and the size and the duration keeps changing. If I had done this figure 5 years ago, you would have almost none of these fires being in the database that you see here on the right. And we also had something that we probably shouldn't be too proud of. We had our first mega fire that was over 1 million acres. So let me try to summarize some of these points. The 8 largest wildfires have all impacted parts of the California Delta watershed. The kinds of things that respond to these kind of burn scars include things like temperature of the water, sediment load, turbidity, dissolved oxygen content, pH, the soluble and particulate organic carbon. Some of these systems turn into black water systems after a fire and a precipitation event. Nutrient contents increase, metals content increases. Natural and human produced organic contaminants are derived from the fire, particularly problematic if it has an urban or an urban suburban interface. And then these aquatic food webs then become altered, and things like harmful algal blooms become an increasing problem for a lot of these systems. Go to the next slide. Oh, excuse me. One last comment I wanted to make about this is that when you have these kind of large fires on the landscape, one of the things that you're often very interested in knowing is how fast will they recover? And is there things we can do that can help with the recovery of the burned catchments? And one of the things that's really critical to improving the quality of the water and improving the quality of the landscape after these big fires is to get vegetation recovery going as fast as possible. And this then scales very nicely into the size of the fire and the intensity of the fire, with probably the intensity of the fire overriding size in terms of some of the water quality effects that you see. Next slide. I could talk about each one of these various contaminants and how they're affected and how water quality is affected. I think to make my point, I'm just going to focus on one specific study that just recently was published, which is an example of some of the kind of things that you see when wildfires on the landscape are intense, large in area. The word megafire is now is commonly used to describe these fires. One example that we actually were not lucky enough to catch with a new network of sensors that give continuous data is an event that occurred on the Klamath River up near the California-Oregon border. Dissolved oxygen sags are usually not seen because most of the sampling and most of the analysis, they are just occasional grab samples. But if you have the kind of new technology that many of these new sensors offer us, you can have continuous real-time measurement being made. And this happened to be a database that was available on the Klamath River. The tribal, the Yurok and the Karuk tribes have a water quality analysis system with continuous sensors that's a byproduct of the fish kills back in the 2000 to 2006 or 7 period of time. This sensor network has been in place now for about a dozen years. And what it allows is that if an event occurs within the catchment, you have a good chance of catching it. And the event that was actually studied was the McKinney fire in 2022. And then the McKinney fire was a large fire, about 160,000 acres. The water quality showed some immediate and strong response to what we are calling a rain on fire event. In other words, the fire was still going, active. Rainfall came in onto the burn scar that mobilized a lot of the ash and charcoal and other kinds of materials that had been burned, moving it into the Klamath River. And that burn scar material produced dissolved oxygen sags all the way down to zero, no measurable dissolved oxygen. And the downstream movement of this material basically was almost 50 miles of degraded water quality, and a fish kill of over 10,000 fish occurred from this event. And this is an example where having the right kind of sensors and having the right kind of network in place allows you to actually diagnose and measure these kinds of significant events. Next slide. So active mega wildfire situations require considerable resources to save lives and to save property. But one thing to emphasize is that the wildfires also are not ended when the fire is suppressed. Fire effects do not end when the fire is over, and it is this post-fire period of time that is a really critical time and timing to get in and assist the vegetation recovery or assist the capture and control of some of this material. A byproduct of these burn scars is that often water treatment facilities are overwhelmed. And so this is one example of keeping tabs of and working on the fire after the fire is actually over. Burn scars are major sources of contaminants. The propagation downstream is something that's very interesting and new area of science worldwide. We're seeing now multiple reports of where the propagation from these mega fires can have water quality effects that are tens to even hundreds of miles downstream. And the one thing that I would point out is something that probably has some need for further study is that most of these burn scar materials end up in a reservoir. About 80% of our water supply passes through a reservoir. These reservoirs, when they're filled up with a lot of this burn scar contaminant material, it is something that we don't know a lot about the reservoirs and the water quality that are affected when the reservoirs are filled with a lot of this burn scar. So far, the networks like the UROC and group network up in Northern California, we don't have those same kind of capacities in other systems. And one of the things that we recommended in our paper is that you look at trying to get more of these types of things going for making these kind of measurements in the future. I think I'll stop there.
Yeah, huge thanks. I mean, you have connected dots that I think a lot of us maybe joining today didn't know connected. And that is the wildfire crisis that we're experiencing, these catastrophic wildfires, these conditions actually impacting our water systems, either, overwhelming local systems or degrading the quality of our rivers, and not only drinking water, but all the life that depends on it. And then that remarkable map that you showed that shows the Delta is draining a large portion of the Sierra Nevada between the Sacramento River system and the San Joaquin River system. So we have to remember that wildfires up in the mountains actually could very well have an impact on the Delta that we're talking about. Is that fair?
Yeah, I think the propagation downstream post-fire is something that we don't know as much about as we should. Certainly in New Mexico, we noted that it was 50 miles downstream. It turned the Rio Grande completely void of oxygen for hours at a time. So it can be a fairly severe effect. And then again, up in the Klamath, it was again somewhere in the order of 60 to 80 miles downstream that these water quality degradation pulses can be measured.
Well, it's helpful to anticipate the risk or the threat of that, just given what we know about accelerating climate change and its worsening wildfire conditions. So thank you. I want to keep you on the screen, Cliff, and I want to bring back the colleagues who have already joined us, or the panelists who have already joined us, as we introduce our final panelist, who is Henry DeBay. Henry has a very important job. He's the Deputy Executive Officer for Science at the Delta Stewardship Council. Remember, the Delta Stewardship Council, led by Jessica, who led off our discussion, this independent entity within state government that's charged with balancing the Delta for nature, for water supply, for the people who live there. So, Henry, I get to ask you the very difficult question of, how do you and your colleagues, the Stewardship Council, take in all of this science from these independent scientists and use it to plan and to make decisions within the Delta?
Thank you, Secretary Crowfoot. Yeah, if I could get my one slide, and James, you can just move to the next one. Thanks. So, as we just heard from the previous speakers, California's future is projected to be shaped by more extreme swings between drought and flood conditions. And so for those of us working in science in the context of water management, like us here at the Delta Science Program, it means we need to help strengthen and accelerate the full science to decision process, from data collection to analysis to action, all while maintaining scientific integrity. And so the graphic shown here on the screen, again from the 2025 State of Bay Delta Science publications, has the 5 key ingredients we think are essential for doing that. So first, I'll draw your attention to the middle of the diagram: collaborative, open, and actionable science. So collaborative science means working with tribes, communities, and agencies from the start so that science is grounded in real needs and shared goals. Open science refers to data that's publicly available and transparent, which promotes innovation and accelerates discovery. Actionable science is research that directly supports decisions, whether that's how we operate reservoirs or where we restore habitat. So in short, science achieves its full value when it's collaborative, transparent, and able to guide action. Second, we need coordinated scientific monitoring of the environment. Monitoring is our early warning system. It tells us when and how conditions are changing. It's like a smartwatch, constantly tracking your heart rate, breathing, and stress levels. It doesn't just tell you how you're doing, it tells you how you're changing so you can act before something goes wrong. And the Delta has one of the most advanced and long-running monitoring networks in the world. It includes everything from precipitation gauges to water quality sensors to scientists on the water sampling for fish. But changes are afoot. Federal agencies are starting to shift monitoring work to private companies or prioritize their own mandates over shared needs. And this does risk fragmenting the system and creating gaps in long-term data right when we need it most to detect climate trends. So that's why it's essential to maintain this monitoring network through strong coordination and stable funding. Third, we need integrated modeling and other innovative data science tools. Models turn monitoring data into insight. They help us forecast conditions and test scenarios to evaluate different management options. For example, models can project how releasing water from a reservoir might keep salty ocean water out of the Delta. And we have many different types of models: weather models, water flow, fish population models, each answering specific questions. And actually, when we use these models or when we integrate them, they provide a far more complete and useful picture of system-wide change. And automation advances in artificial intelligence can also, help run these models in near real time so managers can anticipate risks and make proactive decisions. And this is already starting in the Delta. We're piloting tools like AquaWatch, which uses sensors, satellites, and AI to forecast water quality in real time. And expanding these tools can help us better predict changes in water temperature, harmful algal blooms, and other climate-driven stressors. So in short, integrated modeling helps us shift from reacting to climate impacts to predicting and preparing for them. Four, we need to strengthen science communication. And science communication isn't just about explaining results, it's about making sure the right information reaches the right people at the right time. So that includes scientists working with managers from the start to design research around real decision needs, or managers clearly communicating what decisions they need to make and when, so science is delivered in time to inform them. It also includes decision support tools like dashboards that automatically translate monitoring data and model outputs into clear options with trade-offs, so decisions can be made quickly and confidently. In other words, science communication is about connecting people, tools, and information throughout the entire science to decision lifecycle. And last but not least, we need adaptive governance. And this may sound wonky, but it's a really simple idea. Basically, as you were talking about earlier, Secretary, our systems, laws, permits, policies, and processes have to be rewired in order to flex and adjust as conditions change. So this subway map looking portion of the graphic is meant to illustrate there isn't just one future. We are heading into multiple possible futures shaped by drought, flood, sea level rise, and ecological change. And our governance systems need to be nimble and able to respond quickly. So during wet years, as others have mentioned, we should be able to rapidly redirect flood flows to recharge groundwater or reservoirs, because we know that drought may just be around the corner. And we are beginning to see progress. So permits like the incidental take permit for Delta water operations now include adaptive triggers that adjust management based on real-time science. So we need to normalize this flexibility and tighten the connection between science and management decisions. And this is as much a cultural shift as it is a procedural one. And in closing, I know we're getting super close on time. I just want to underscore we have the tools, we have the partnerships, we have the scientific capacity in the state to meet the challenge of extreme events. The task really before us is to continue to invest in these tools, to connect them, and to make sure we're working together so we can adapt in real time. As I said earlier, all of this is available in the State of A Delta Science publication, so check it out.
Wow. Henry, such a powerful way to kind of bring this conversation together. And Obi and Sasha and Cliff, I have to give you so much credit for breaking down complex science in such a short amount of time. I'm super proud of the work that the independent science board of the Delta, the lead scientists, the stewardship council are doing within the Delta. To me, like, this is a great model of how we take, some of the most sophisticated science in the world and make it actionable for our decisions. Jessica, maybe ending with you, there are a lot of obviously big questions before the Delta, whether it's, proposed infrastructure projects like conveyance, or questions of fisheries management, or how we protect communities along the bay. How does the Delta Stewardship Council as an independent entity, how do you leverage this science as you kind of make these decisions on whether projects or actions ultimately are in line with the state's, co-equal goals?
Yeah, thanks for that. Yeah, just quickly, our management plan, the Delta plan, does have a legally enforceable component. So we actually have regulations or rules that projects in the Delta must follow. And we do have one of those regulations is a requirement that a project use best available science and document that science to show that they've really thought it through and that people can, check the math. And so, that's one of many ways, but that is kind of a where the rubber hits the road way that the council ensures that best available science is guiding Delta decisions.
Wow. Well, I have to say, at a moment when some are calling the importance of science into question, or questioning, what extent do we need things like climate science to help protect our people and our resources, I think you all stand as a real beacon, maybe a paragon of how we should be integrating science and decision making. So Obi, Sasha, Cliff, huge thanks for contributing some of your career and expertise to helping us manage the Delta. Of course, Jessica and Henry, the entire Stewardship Council, thank you for what you all do. We've had really almost 250 people join us here today, and I'm hoping that almost everyone, just like me, learned a ton from you all summarizing the work that's happening. So thanks so much for all you do. And I'll just share one last slide. If anyone who's tuned in has any follow-up questions or suggestions for us, either in relation to this discussion or suggestions for other such discussions in our speaker series, please hit us up at this email, secretarysuggestions@resources.ca.gov. Again, thanks so much for all the work you do, and hope to see you on down the road.
Thank you.